Okay, so today I'm very happy to introduce Professor Han Zhao. So Dr. Han Zhao is currently assistant professor of computer science and by courtesy of electrical and computer engineering at the University of Illinois Urbana-Champaign, stands for UIUC. And he's also an Amazon visiting academic at Amazon AI. His research interest is centered around trustworthy machine learning with a focus on algorithm fairness, robust generalization and the distribution shifts, and the model interpretability. So today, he will talk about revisiting scalarization in multitask learning. So then let's welcome Han.
Yeah, thanks everyone again for taking the time to participate in this discussion. So I want to make this talk more interactive and casual. So during my talk, if you have any questions or any part that is not clear, please just feel free to stop me and then we can discuss. Today I'm going to talk about a line of approach called multitask learning. But before that, I want to give a very quick overview about what is machine learning. So Professor Thomas Zhao, who is one of the early pioneers in this area, he actually once gave a very intuitive and high-level definition. So essentially, the notion of machine learning encompasses three components. So it's like follows: computer program is set to learn from experience E with respect to some class of task T, and then performance measure P, so that if its performance at task T as measured by P improves over experience E. So here the three main components is experience, performance, as well as task. So let me just give a quick example to illustrate a typical machine learning pipeline, how it works. So the three components essentially corresponds to the three phases if we try to build a typical pipeline. So the first experience essentially corresponds to data. We need to collect the data in order to train our model. And then once we have the data, we know what the problem we are trying to solve. That means we also need to define a so-called performance measure corresponds to the P. And the P can tell us whether my model or my algorithm is doing a good job or not. Now, the central job of machine learning researcher or practitioner is to design what kind of a task we try to design and tackle in order to improve with respect to the performance P from my data D. For example, if I want to follow this pipeline, what people usually do is we will ask some domain experts to help me to extract corresponding data in practice. Once we get the data, we somehow represent the real world data, for example, documents or natural language tags, into some representation that can be understood by a computer. For example, in computer, every kind of document can be represented by a high dimensional vector. And because the document can be very unstructured, but if we transform into high dimensional vector, those vectors can be understood by a typical computer program. And the computer program can just deal with those high dimensional database, and then according to the performance measure, we can try to solve the task of interest. So if we use a typical example for example, in biology, a typical task is we try to guess from the MEG data, which is essentially the scan of our human brain, to try to understand what kind of object or concept we're thinking about. Now, in this kind of application, the typical data we're dealing with is, say, a three-dimensional RGB image corresponds to the activation activity at the brain, the MEG data. If I try to approach the problem of taking the MEG data as input and then guess what a specific person is thinking about, then I also have the so-called representation for each of the words in the dictionary. And then the problem of trying to, say, guess what a specific person is thinking about when reading the MEG image is we try to match the corresponding representation of a word to the corresponding MEG data. If we can build such a correspondence or mapping, then it says that we can actually try to achieve this problem. Another typical application is, for example, in finance. The finance stock prediction problem is actually a pretty mature field nowadays in real world. And then for this kind of problem, the typical kind of data we're dealing with is the stock price. And for example, we have the observation of S&P 500 in the past 10 days. And then those corresponds to a curve, a temporal curve. And then the problem now becomes, given the past 10 days price, I try to predict what's the immediate price for tomorrow. So that's also a well-defined problem. In this case, the data we have is all the past fluctuation of return in the price for a specific stock. And then the goal is I try to see whether my prediction for the price of next day is accurate or not. Of course, I mean, with machine learning being more and more powerful, essentially we have the capability to select more and more large scale data and build larger and larger models. Those kind of application has also been used in a lot of high state domains involve human beings. For example, in the United States, those machine learning models have been used in, for example, in Amazon during the hiring process. So when applicants upload their resume, the resume will not be read immediately by a human resource, HR. That's because there are just too many applicants, and we'll try to reduce the human efforts in this process. So a typical process is that PDF, which is potential unstructured document, will be transformed into a vector, which is essentially a description about each of the aspects of the applicant, like the education, the prior work history, the age, the expected income level, etc. And such representation will be processed by an automated model. Another application scenario is about student loan application. For example, it's very typical in the United States for college students to apply for student loan in order to continue their higher education. And then for those scenario, each student will also fill a form. And then the form will be converted into a representation and then processed by a decision model. So in both cases, the decision model, the input can be just a description of an applicant, and the output is a binary decision. Say for student loan, whether we accept or decline the loan, and then for hiring process, whether we want to stop or proceed along the hiring decision-making process. And as we just described, those kind of applications are very high state because a potentially negative outcome or incorrect prediction can lead to a drastic influence on the specific human beings. And my research is essentially centered around trustworthy machine learning. I know it's a very vague word, but more detailed speaking, it encompasses 4 aspects: robustness, fairness, privacy, as well as interpretability. So I will not go into detail about each of the components here, but essentially, I try to say, let's go beyond just the efficiency as well as the accuracy of building machine learning model. And especially in high state domains, we should, beyond the accuracy, also aim to achieve privacy, robustness, fairness, etc. Okay, so that's a quick overview, but a common theme for all those lines of research is, so we have multiple objectives we try to optimize for. Traditionally speaking, for example, we're only interested in optimizing, improving the accuracy, but now we also have another dimension. Let it be, say, fairness or interpretability or privacy. And the talk today is try to understand, is there any potential trade-off between those different multiple tasks or objectives? And then if there's such a trade-off, how can we try to achieve the optimal trade-off between those different tasks? Okay, great. Now, let's dive a little bit detail into this kind of typical machine learning process. Here we, as we just mentioned, we use 2 examples to illustrate a typical scenario. It's called a regression. So regression basically says that we try to build a model that takes a sort of like either image or stock price as input, and then output a real number is my prediction. So here, for example, for stock prediction, the output of my model will be the return or the price, so which is a continuous real number, right? And then I need to find a way for me to measure the performance. Recall there are 3 components. We specify the data, and we specify the task, but I also need to specify what kind of like performance measure I want to use. So that means if I follow the pipeline, so later we will describe how to choose my model. So the model is essentially a function, f. So the function f will take some input x as the information, and then produce some prediction. So whenever I use a hat to y, that means a prediction. And whenever I use y, I mean that's the ground truth label. For example, if I try to check what's the stock price information, I can collect all the past 10 days as my input. And then in retrospect, I can also collect the next day's price as the ground truth label, right? And then I have a prediction and also have a ground truth label. I try to measure how good it is. So that means for this kind of problem, I need to first define how can I measure the goodness of my fit. And typically for regression problem, a loss is I just measure the difference between my prediction and the ground truth label and take a square. That's basically the mean square error. Now, since I have a batch of training data points, so what I can do is I can take the mean across all the training data points. So recall, when I try to build a model, I collect the data so that I know the ground truth response. I also know my predicted response. And then I can measure each of them and take the mean. Great, so that's the typical loss. Now, we now move to the second question. So we have specified the data we're going to use and specified the loss function. Now, how about the model? Right, so for the most simplest case, the model is just a linear model for regression. And we all know that for example, in statistics, that's ordinary least square problem. And the idea is that we collect enough data and plot, for example, plot in a 2D plane. And then I try to fit all the blue dots using a straight line. All right, so that's not, and there's a closed form solution for those kind of problem. Although the figure here only shows, say, the input is one-dimensional. But in practice, you can make it more abstract. Say it's a high-dimensional input. For example, in stock prediction, you can collect all the past 10 days data so that the dimension of X is 10, right? And this kind of like a model can also be generalized to a classification problem. And this brings us to the realm of neural nets. And here, let's go start with the simplest model. It's called a perceptron. A perceptron is actually developed by Dr. Frank Rosenblatt. It goes back to 1958. It's essentially a linear model, but we can actually use a neuron diagram to simulate this kind of linear model. So imagine I just enumerate all the input as one of the neurons output in the previous layer. So one for each of the input dimension. And then all those signals will be converted or transmitted through the synapses between two different neurons. And each synapses will have a strength. The strength corresponds to the weight of the connection between two neurons. And then once the central processing unit of the neuron of interest takes all the input, I essentially measure the strength of the activation. And the strength of the activation is essentially I take the input multiplied by the strength, and then check whether it's larger than 0 or not. It basically say whether the combined strength from all the connecting neurons has surpassed a threshold or not. If it's past a threshold, then I say it's activated. It's activating the current neuron. Otherwise, it doesn't. So equivalent to that speaking, we're using a threshold function. The threshold function is if it's larger than 0, the output is 1. Otherwise, it's 0. So that's the simplest case. Let's say called the perceptron model. If we think about it, it's essentially define a linear classifier. So imagine, for example, if I try to predict all the cats versus dogs, and then it's essentially say, let's describe all the cats and dogs on the 2D plane. Those correspond to those 2D points. Each color corresponds to one category. And I try to use a linear straight line in this 2D plane to partition these two categories. Of course, I mean, I can have infinite many different choices of those straight lines. And the question is, which one should I use? And that corresponds to the question of designing an algorithm to try to find the best of such linear plane. Now, but there's still problem. The problem of this model is, as we can see, mathematically this just corresponds to a linear model. For example, for these two categories of data, I cannot find a single linear line which perfectly separates the two categories. So a natural question is, how can I extend this kind of simple model by using a sort of composition, which leads to the simplest type of neural nets. And the first change we are doing is, instead of using a step function, which is not smooth and not continuous as 0, I make it more smooth, right? So that's the first change. And in practice, there are many different choices of such continuous functions. And throughout the presentation, I will use phi to denote the activation function of each neuron. So the activation function essentially says, given the input, I change the output of the neuron corresponds to apply the activation function to the input. For example, originally we have a step function which is not smooth, but now I can change it to the sigmoid function on the right-hand side. You see the sigmoid function is continuous because it's essentially an S-shaped curve, and we can choose the slope at the 0 point to better approximate the original step function. But different from step function is it's differentiable and continuous. So that's the first extension. The second extension is we can actually compose all the neurons together, layer by layer. For example, each circle, blue circle here, corresponds to one neuron, the simplest model developed by Dr. Rosenblatt. And we know that's not powerful enough. It essentially corresponds to linear classifier. But what if I stack all the neurons together layer by layer? And then to each layer, I have multiple neurons. And this idea is actually very powerful in the sense that originally it's a linear classifier, but by stacking multiple layers of neuron together, we can show that it can solve arbitrary nonlinear classification problem as long as the decision boundary is smooth enough. But mathematically speaking, if we abstract out all the details and use an equation to describe what the prediction model is, suppose our input is d-dimensional feature. And then we know that each neuron is doing a weighted sum of the input. And that weighted sum essentially corresponds to an inner product between a vector and another vector. Right? If you think about weighted sum, that's computing the dot product. And if I have multiple neurons, that means I can stack all the weights of the neuron into a matrix. Let's call it W. And then whenever I multiply W by the input X, that corresponds to a propagation of information from the last layer of neuron to the next layer. And then after each propagation, I apply an activation function phi. So that's a nonlinear activation. And I can repeat this procedure for multiple layers. And the equation I show here is essentially the simplest two-layer neural nets, because the X is my input, and then the phi of Wx will be the second layer. Because whenever I apply a phi and the matrix multiplication, that corresponds to one layer of transformation. And then the thing we need to pay attention to is the shape of the matrix W, because here D corresponds to the number of neurons in the input layer, and the Q corresponds to the number of neurons for the next layer. And for this particular two-layer model, we only have two layers, and the output layer is just one dimension, because V is a vector. So that means the second layer is I connect the output of the first layer to a single neuron is my output. Of course, we can try to extend this procedure for many, many layers. So the most general formulation for a neural network in this scenario is, so whenever we have an input X, I stack into a matrix W, and then apply a nonlinear activation function. And then I repeat this process recursively for L different layers. And the end of the L layer will just be my final prediction for the neural nets. And then the model parameter is essentially the weight of the neural network I try to optimize for. In this case, it's from W1 to WL. And the shape of each WL determines the number of neurons I'm going to use during my modeling process. And although this particular formulation is only for regression problem, but it can be actually slightly changed into classification problem as well. For example, if I try to give an image to classify which category it belongs to, suppose I have K categories, and that just means I transform the original output of the neural network by the so-called Boltzmann distribution. So the Boltzmann distribution takes any real value as input and then transform into a probability distribution, right? So that's the very basics of neural network in general. Essentially, that's a layer-wise transformation, linear transformation plus nonlinear activation. But the topic we're interested in today is called multitask learning. So what's special about multitask learning beyond the traditional neural network is given the input, we try to solve multiple objective functions simultaneously, not just one. A typical scenario is when we try to design self-driving car, the intelligent module corresponds to a module which takes image as input. But at the same time, I try to solve three tasks. For example, given an image about the current street scenario, we try to essentially understand what's the depth of all the objects in this image. And then also I try to detect whether it is a pedestrian in this image. And so the first task is about the depth understanding. And the second one is a pedestrian detection. And then for each of these tasks we're going to solve, it's based on the same input. So that means I'm going to design a neural network procedure, a model that can simultaneously solve those multiple tasks. So how can we implement using the diagram we just described. So the conceptual framework is, given the same input, I have 3 branches. Each branch corresponds to 1 task. So that means when we design a neural network, we can also design in this way. So that means given the X is input, in this case, an image, I just apply the nonlinear neural network we described to transform into some of the so-called feature. Because one way to understand what neural network is doing is it's essentially doing a sequence of feature transformation. So the input level is the original input, and each layer corresponds to one particular nonlinear transformation of my data. And now I can apply those kind of transformation layer by layer. Now, if we use this kind of perspective and go back to this model, and this model, what it's doing is I try to use a common feature transformation to get some intermediate feature. And then I hope that this intermediate feature is useful enough so that it can be simultaneously used for the 3 tasks I'm going to solve, where each task corresponds to a specific neural network for the prediction problem. And in terms of formulation, that means the data set we have is in the form of xj, yj, but 1 for each of the tasks, I. And I have k tasks simultaneously. For each task, I can potentially use a different loss function. For example, for depth understanding, the task is about regression. I want to understand the depth of each pixel. So that means the output of the first neural network would just be a pixel-wise real value prediction problem. And then the second one is about pedestrian identification. Then the output is just say binary classification 0 or 1, whether it is a pedestrian in an image. Now, when we try to design such a model, it's very generic. That means whenever we have a multiple task, we can always try to build such a model to solve those multiple tasks together. But there's a key question. The key question is that always beneficial to train a single neural network to solve multiple tasks simultaneously? And in practice, people find there's a phenomenon is called negative transfer. So what does that mean? So that means if I try to use this kind of model, I mean, ideally, if this procedure is successful enough, we just want to build one huge neural network that can simultaneously solve all the tasks I can think of. That would be the best scenario. And that would just be a super general artificial intelligence, which can perhaps help humans solve all the tasks. But now, what people find is it's not always beneficial to train all the tasks together using a single model. And that particularly refers to a negative transfer problem. So one of the key questions we try to answer is, when will negative transfer happens? And how to decide whether I want to combine 2 data sets when training a single model. Great. So if we see how can we approach this problem, suppose we have k tasks, it's essentially that for each of the tasks, we have a loss function defined by Li. And then the inner summation goes through all the training data for OIST task. And then I have one loss function for each task. So I take just the average loss for each of them. So of course, that's the simplest case. And actually one of the most frequently used formulation. So here, the optimization is G and HI. So G corresponds to the shared multitask feature I try to learn. Because the goal is I try to learn a single feature that is simultaneously helpful for multiple tasks. And then once I get the feature for each of the tasks, I want to learn a prediction itself, right? So that means once given the feature, I can have different models for different prediction. That's totally fine. And if we think about the problem is, essentially, I have a multi-objective loss. That means for each of the loss function, I have one component. And if I have a k task, then the underlying problem is a k-dimensional minimization problem rather than one-dimensional. And then if we take this perspective, say the original problem we try to solve is multi-objective minimization, but multi-object minimization is not easy to deal with, mainly because we cannot always compare 2 vectors in terms of which one is larger than the other, because it's not a total ordering. So we need to find one way to reduce the multiple objective into a scalar. And this is called scalarization. The idea is that whenever I have multiple loss function, I can specify a preference vector, let's call it W. So the preference vector is essentially a non-negative vector which sum to 1. And the relative scale of this preference vector, meaning how much importance I want to pay for each of the tasks, right? So for example, in the original formulation, that just means I pay equal attention to each of the tasks by assigning 1/k to each of the laws. But if you have a preference over one of the tasks, we can actually assign a larger weight for the corresponding task and a smaller weight for the remaining ones. So that's by using different preference vector here, we essentially specify our preference for the model choice. So let's see a geometric interpretation of using this approach. So if we use this kind of scalarization technique to reduce the original multi-objective optimization to a scalar one, that means what I'm doing is I just change the loss function from 1/k to wi. Because wi is the weight assigned to the i's loss function, right? And then I just, again, take the summation across all the loss from I from 1 to k. So that's the idea. But if we look at the geometric implication, so what this approach is doing is, in the case of two tasks, and for each task, it corresponds to one axis. But the tasks, they are not necessarily compatible with each other. So that means I cannot always achieve the origin. The origin is the optimal point, because the physical meaning of the origin is I find a model which is simultaneously optimal for both tasks. But the more traditional or classic frequent scenario is whenever we try to reduce the error for one of the tasks, inevitably I have to increase the loss for the other. So that means all the feasible solution actually corresponds to this shaded area, the blue one. And whenever we specify a preference vector W, that just means I specify a direction. And I try to find a model which is optimal with respect to this direction. All the model on the boundary of this feasible region is called Pareto front or Pareto optimal, meaning that I cannot always compare which one is better. Everyone on the boundary is optimal in a certain sense. And then if I want to choose one specific model, I just need to specify the W. Once I specify W, the point which is cutting or tangent to the W vector will be the solution. All right. So it seems so far so good because there's no loss of using this approach. That means whenever I try to choose a model, I can just specify the corresponding W vector. So the question is there any like a potential downside or limitation using this approach? The answer is yes. So let's see these two figures. So the left figure is a pretty ideal scenario, meaning that all the feasible region is convex. So suppose the feasible region is convex, and then I know the blue part is my feasible region, and I only care about the green line because the green line corresponds to Pareto front, meaning that every point on the green line is optimal. And whenever I try to achieve a point on the green line, I just need to find the corresponding normal vector. That's good. But the issue is, in practice, the feasible region is not always convex. For example, on the right figure, still all the points on the green line are optimal because they are still Pareto optimal in the sense that no other points dominate them. But now if I try to achieve a point, for example, between A and B, I cannot achieve it using the cutting plane method. The reason why I cannot achieve it is because if I, for example, want to achieve this point, then whenever I choose the corresponding normal direction, the normal direction will only intersect A or B. Because A and B are the optimal solution given the choice of the preference vector. But A and B, the physical meaning is, for A, it's very good for task 1, but it incurs a very large loss for task 2. And for B, it's actually pretty good in terms of task 2, but it's very large for task 1. So that means whenever the feasible region is non-convex, then if I just try to use a scalarization method, then I either have to pay a high price for the first task or pay a high price for the second task. And that's actually provides one potential explanation. Yes.
So usually we have a feasible region is non-convex or like convex?
Yeah, that's the question we try to answer.
Okay.
That's right. Yeah, that's actually one of the key key research question we try to answer, right? So you see that these are the two distinct criteria. So if the feasible region is convex, there's nothing lost using the scalarization. But if it's non-convex, that means we have to pay a price. And because ideally I want to achieve the middle point. The physical meaning of the middle point is it performs reasonably well for two tasks simultaneously, but I cannot achieve that using scalarization. So the question we want to answer is, let me skip this part because we do not need to go into this technical detail. The key question is, how can I design algorithm, even if the region is non-convex, to try to achieve a balanced solution? Right, so let's try to first answer this question. In practice, this actually has been the focus of multitask learning in the last decades. And there are actually hundreds of different papers being written, propose different algorithms to try to solve this problem. But we can see one reason why using scalarization have such a limitation is we're actually using the fixed preference vector across all the optimization trajectory. So that means when I try to search for an optimal solution, I'm always searching along a single direction. That's the limitation. But we do not have to use a single direction for search. We can use the so-called adaptive method. The idea is that I'm actually changing my preference vector at each iteration. So how can I do that? So the idea is that we know the gradient is very informative for each of the tasks. The gradient provides us the steepest ascent direction locally. And now if we just use a single fixed preference vector, that means I'm trying to just use the average of the gradient if I have two tasks, right? Because that's, if I move along the 1/2 G1 plus G2, that corresponds to minimize 1/2 weight for each of the loss. But actually, we can change this criteria. That means for different G1 and G2, I'm trying to find a direction D so that I'm trying to move along the direction D. And the direction D will change across different iteration. So there are many different algorithms try to do this. I will just go through the first one. The first one is called multiple gradient descent. It's actually the first algorithm along this line of work, which inspired all the following works. So the idea of this MGDA is, suppose I have multiple tasks, and each task represents by a gradient direction. That means the local steepest improvement direction. And I try to find a single direction D. And then if I use a fixed preference vector, then D is fixed according to the coefficient. But now I'm not doing that. I'm trying to find a direction so that I satisfy this criteria. So let me explain what's the meaning of this criteria. So whenever I compute the inner product between the gradient and the D, that's actually called the directional gradient. So that means if I move along the direction of D, how much improvement in terms of loss function I can try to achieve. And then I try to find direction D so that even for the worst task, it has the maximum improvement. So that's one of the criteria. And that means suppose I have multiple tasks at one iteration, and then I try to determine which direction I should try to choose. Then I try to say, let's find a direction so that even for the worst task, I can see the maximum improvement. So that's the criteria. And that's the criterion. It's called so-called primal problem, but we can always try to find a dual problem. And it's easier to see why it corresponds to adaptive algorithm from the dual perspective. Because if we compute a dual problem for the primal problem, then it's equivalent to say, given all the gradients K from K task, I try to find the coefficient alpha so that after the aggregation given by alpha, this norm is minimized. So you see that means if I have different gradient direction G1 through GK, the optimal solution alpha will change. And that reflects the meaning of adaptive because we're not using the single alpha. As compared to the previous method, at each iteration, we'll always use the single alpha, which is W. But in this case, we're using different alpha. And geometrically, that means if I have two directions, then I try to find perpendicular line that is perpendicular to the subspace spanned by all the gradients. And that would be my solution because this red line corresponds to the minimum norm of this problem. And at each different location, I will have different combination alpha. So this line of work has been the dominating research in the past decades, at least for academia, right? But what people actually, especially from Google, because they have the capacity to do very large scale experiments, what they find is, suppose I build my model large enough, and my training data large enough. And they find that in practice, actually, there's no benefit of using those kind of sophisticated algorithms than just using a single preference vector. And in particular, what they show is, here we have two figures, and they do very large scale experiments. Here, the number of parameters in those neural networks, hundreds of millions to billions. And they show a curve. So here on the left-hand side, the blue curve corresponds, each dot on the blue curve corresponds to using a fixed preference vector for two tasks. And then by changing the preference vector, we can draw the so-called Pareto front. And then each of the other shaped dot corresponds to the particular algorithm designed by academic community using more sophisticated methods. And what they find is, actually, indeed, those specifically designed algorithm adaptive weighting methods can achieve a pretty good trade-off between two tasks. Because if you see the conversion point, that's actually in between the two extremes. But on the other hand, it's not better than existing search method using the blue line. And what more surprising or interesting is, this kind of tendency becomes more and more obvious if they make the model larger and larger. So on the right figure, what they do is they verify, they change the number of layers, essentially the number of parameters in the neural network. And they find that if you increase the number of parameters large enough, then the Pareto front actually corresponds to a direct angle, 90 degrees. So that's actually pretty surprising, because if the Pareto front is more and more towards the origin, that means it's convex, and there's no loss of using fixed preference vector. And theoretically, there's only advantage of using adaptive method if it's not convex. But what people find is, if you make the neural network large enough, the Pareto front will be convex, at least empirically. So what we try to answer is, let's answer this question from a theoretical perspective, in the sense that for neural networks, and then if I try to understand the Pareto front of multiple loss functions, I want to understand when will the Pareto front be convex and when it will be non-convex. If we can answer this question, then it can help us, say, try to search for the correct model architecture, or I know how large my model needs to scale to in order to avoid the potential limitation of using a fixed preference vector, right? And then one existing result people know is, if each of the loss function for each of the tasks is convex, then the Pareto front will be convex. That's a folklore result in convex analysis. But the problem is, for neural network, even we use linear neural network, the loss function is non-convex, right? So this theorem does not apply. So let's start with the simplest case. Suppose we deal with a two-layer linear neural nets. That means the model given by our neural network has the following form. So it's X transpose W times AI. So W is the shared model parameter, essentially the first layer. And then I try to learn a representation. And then once we obtain the representation, I use each AI to denote the prediction for each task. Of course, I mean, each different task will have different AI. That means for the ith task, the loss function will just be the mean square error. And it's X matrix X times W times AI minus YI. So here I use the matrix notation X because I stack all the input vector into a huge matrix. So that means the dimension of X is M by P. P is the input dimension. And the shape of W is P by Q. Q means the number of neurons in the second layer. And then once we have the Q representation in the second layer, we go through AI, which is a vector, Q-dimensional vector, to produce the final output. And then I can measure the performance by comparing to the YI. Right? So that's the loss function of my ith task. So note that although we only restrict our attention to two-layer neural nets, but it's actually the most generic one for linear models. Because even you have more than two layers for linear neural network, you always condense than into just 2 layers. Because if you have multiple matrix multiplied together, you can always condense it into one. So there's no loss of generality if we would just start study a like 2-layer neural network. And the first conclusion we show that is that, so in the over-parameterized regime, meaning that if your neural network is wide enough, so how wide is that? You only need to guarantee the number of neurons you want to use for the second layer is larger than the number of tasks. Suppose your number of neurons in the second layer is larger than the number of tasks, then there is no loss in terms of using fixed preference vector. And then in particular, we can actually show a stronger result. The stronger result shows that if that's the case, then actually your Pareto from reduced to a single point. So that means that's a right angle, 90-degree angle. That's the theoretically optimal solution. Because if that's the single Pareto from, no matter which preference vector you're going to use, you're always going to converge to this point. And that's actually, at least empirically, consistent with Google's observation. You see that if you increase the number of parameters, then the Pareto from ND points to a 90-degree tendency. So that's the first conclusion we show. So we wonder why that's the case, because it seems to be too good to be true. Due to the time constraint, I will not going to show the proof idea. But the idea is that if your neural network is wide enough, and then we're using a linear neural network, then the prediction loss with respect to the ground truth label can always be decomposed into 2 parts. So the second part is the approximation error, and that's a constant. It has nothing to do with how I design my model parameter. And because y hat corresponds to the optimal linear prediction I can get, no matter what kind of model I'm going to use. So I only need to care about the first part. And the first part is the fitting loss. So that means how good my neural network can approximate the optimal linear prediction. So this is true only for mean square error, because that's essentially a form of Pythagorean theorem. It basically say that the mean square error can be decomposed into 2. And then since the second term is a constant, I only care about the first term. And the first term, if my neural network is wide enough, then I can simultaneously solve this equation for k times. Because here, this part only corresponds to the ice loss function. But if my neural network is wide enough, I can solve this equation for each of the I, k. And the limit of the width is only k. That means if my number of neurons, q, is larger or equal to k, I can simultaneously solve all of them precisely. And that's the theoretically optimal solution we can try to achieve. Okay, so that's the first case. But now how about under-parametrization regime, meaning that I cannot design my neural network to be wide enough. So my number of neuron q is strictly less than k. Now in this case, is there any loss? And the answer is yes. Basically, the specific conclusion we will show it later, but it basically says that in general, if your neural network is not wide enough, then the Pareto from is non-convex. And it only becomes convex if all the tasks are positively correlated to each other. In particular, more precisely, we studied 2 scenarios. The first scenario is your neural network is extremely thin, meaning that you only have 1 neuron in your second layer for your representation. And the other extreme is your neural network is only mildly under-parametrized, in the sense that the number of neurons to be used is k minus 1. So recall, I want q to be smaller than k. So q equals to k minus 1 is the maximum number of neurons I can choose. So in both cases, we can show that unless all the tasks are positively correlated, and the correlation is given by this inner product, y hat transpose times y hat, corresponds to the relationship, unless this matrix is element-wise non-negative, otherwise it's non-convex. Great, but that's pretty interesting, right? Because the meaning of this matrix G, in the sense that the ij's element is essentially measure the inner product between y hat I and y hat j. But both y hat I and y hat j only depends on the underlying, sorry, it seems it's theory. But both y hat j and y hat I only depends on underlying data. Interesting. Try to close it. Great. So that means if the two task vector actually have positive inner product for every pair of tasks, then this matrix G will be element-wise non-negative. And if that's the case, the Pareto front will also be convex. So that's the implication of this theorem. So let me briefly go over the proof idea why this is the case when the neural network is under-parametrized. So the key idea is that if we try to solve this problem, it's equivalent, not that when we solve this problem, essentially we're trying to solve for W and A. But for each fixed W, there's always an optimal solution for A because the underlying model is linear neural network. So that means we're equivalent to trying to solve this problem, optimizing for Z. Z is my features of the first layer. But if you're familiar with the literature of linear regression, this matrix here is just a projection matrix, this particular form, project to the column space of Z. And so that means the first term is the projection of yi hat to the column space of Z minus the original vector. If I want to minimize this distance, that means I try to find a subspace which spans the original yi hat for each of the I. And that corresponds to, if I try to solve this problem, I want to just try to find a projection matrix PZ so that I want those k-dimensional vectors to be maximum simultaneously. But I have k dimension, and the number of neurons I have in PZ is only Q, and Q is less than K. And that's a constraint. And equivalently, that basically means all the actually feasible solution will be the boundary and the interior of ellipsoid. The reason why it's ellipsoid is because since PZ is a projection matrix, it's idempotent, meaning that PZ equals to PZ squared. And then I can do a reparametrization, say I define each of the TI to be PZ times yi hat. And then if we do this kind of a reparametrization, because the rank of PZ is upper bounded by Q. And for projection matrix, the sum of the rank is equal to the trace. Because for projection matrix, the eigenvalue is only 0 or 1. So if you compute the rank, it's equivalent to the trace. And now if that's the case, then it satisfies this equation. And if you're familiar with geometry, this is ellipsoid in terms of T. Because it basically says that all the sum of Ti squared divided by some constant is upper bounded by another constant. In a special case, if all the yi hat has the same norm, that's just a ball, a high-dimensional ball, a k-dimensional ball. But in general, it's an ellipsoid. So that's characterized the boundary of the Pareto front. But that's only one part of the story because this kind of equation is invariant if we flip all the yi hat. So that means the overall Pareto front is not just one ellipsoid. It will be a union of 2 to the k ellipsoid. And that corresponds to the problem. If the boundary is only one ellipsoid, we know that ellipsoid is convex. So there's no problem. But the issue here is that it's actually the union of 2 to the k different ellipsoid. Suppose I have 3 different tasks. Then actually 3 different tasks, I can draw 4 different ellipsoid. There's a symmetry. So it's like 2 to 3 is 8, but there's a symmetry, so I divide by 2. And there are 4 different ellipsoid. And the Pareto front will be the union of them. Now, if we look at the intersection of 2 ellipsoid, the intersection point will be non-convex. In the sense that each of the ellipsoid is convex, but as long as they have intersection, then this point cannot be achieved because it's not on the boundary of a single ellipsoid. It's simultaneous of 2 ellipsoid. Great. Now, so we answered the question, the first question we tried to answer, say, when neural network will be expressive enough so that you do not need to worry about the non-convex issue. And the answer is, if your neural network is wide enough, then you do not need to worry about that. And if your neural network is only slightly under-parametrized, then there's a problem. So now the question we try to answer is, if somehow we do not have the computational resources to build a very wide neural network, how can we rescue? And the idea is that we can use the idea called randomization. So roughly speaking, randomization is doing convexification. The reason why it holds is because if I have two loss functions, and then I randomize between the two according to some uniform distribution, then if I look at the expected loss, the expected loss will be a convex combination of the two original loss. And that's by definition of the uniform distribution itself. But the first part will just be the original loss function of the multitask learning. And the second one will be the loss function of the second multitask learning. So that means the Pareto front or the loss function of this randomized neural network will be convex anyway, as long as we use randomization. So that's one way to fix the problem. And the second way is actually perhaps more interesting. It's called, we do not use linear scalarization, but instead use the so-called chip shift scalarization. So what does that mean? So again, we start with a preference vector W, but instead of doing the summation, I'm doing the maximization. So I replace the summation over all the I to be taking the max over all the I. Right, so originally we're taking a sum. Now I do not do the sum, I just do the maximization. So it seems to be a very small change in terms of the objective function, but we can show that if we use this new formalization, then every weakly Pareto point on the Pareto front corresponds to a solution of one choice of W under this new formulation. And this is nice. So that means no matter how small scale or how narrow your neural network is, as long as we use chip shift scalarization, there's no loss of generality. So that means even for the non-convex case, if I want to choose or converge to specific points on this green curve, I can always find a W, so that the solution of this red point corresponds to solving the chip shift scalarization under the W. That means I can still, by varying different W, try to search or scan all the points on the Pareto front. Great. Now, so the last question we try to answer is, so far we only talk about linear neural network. That's very limited because in practice, no one uses linear neural network. So does the same conclusion hold for nonlinear neural net? And the answer is yes. So what we show is that even for ReLU neural network, as long as your neural network is wide enough, it's just in this case, the number of neurons required is much larger than the linear case. If anyhow, we can make our neural network wide enough, then there's still no loss of generality. Note that this is only an upper bound, and the upper bound we give is Q is at least as large N times K. That's very loose because it depends on N. N is the number of data points, and usually nowadays it's at least 1 million or even 1 trillion. So that's not realistic. But theoretically, that basically shows that still we have the same phenomenon. Say, as long as the neural network is wide enough, there's no loss. But we don't know what's the corresponding lower bound. Say, what's the minimum width you want to have to ensure convexity? For linear case, we solve the problem because both answer is K. That's basically say K is a phase transition point. But for nonlinear neural network, we only show NK is sufficient, but we don't know the necessary width. But nevertheless, we can try to empirically verify whether that's the case. And indeed, that's the case. So what we do here is that we train a nonlinear neural network for 3 tasks. And each task corresponds to one axis here. And we use very under-parametrized neural network, meaning that we only have 1 neuron. And what we find here is that if we use scalarization, it can only converge to the boundary of the feasible region. So that's precisely the phenomenon we observe if we only have 2 tasks. And as a comparison, the specifically designed adaptive method can converge to the interior. And if we see another algorithm, that's still same the case. Meaning that if your neural network is severely under-parametrized, then it cannot achieve all the feasible solution. Yes?
Do you have any empirical evidence that this
Q N times K? We don't have empirical evidence. We only theoretically prove that. But
do you have any empirical guess?
You mean the lower bound, right?
Yeah, exactly.
I think it should be a polynomial function of K. It should not depend on N.
And it should be dependent on activation.
And that may be, but we only focus our attention on ReLU network. Yeah, very specific one. So this upper bound is for ReLU network. And it's actually not hard to prove this because it's essentially using the memorization capability, meaning that if a neural network is wide enough, and you can design one neuron to memorize one training data point. And since we have k different tasks, each task has n points, we can precisely memorize all the training data points. So nk will be sufficient. But we don't know the lower bound. At least I want a lower bound does not depend on n. But as long as it depends on n, that's bad, because n is very large. Okay, great. So that's basically the summary of this work, meaning that we try to answer when it's sufficient to use linear serialization. And if it's not sufficient to use linear serialization, what other kind of algorithm technique we can use to circumvent the non-convex issue in when we deal with multiple objective function. There are many still interesting open questions. For example, the scenario we focus here is a regression problem, meaning for technical convenience, for the decomposition property for mean square error. But for classification problem, which is usually cross entropy, such property does not hold. So it's not easy to extend the current proof to classification. And also, is there a similar phase transition for nonlinear models? For nonlinear model, we were only able to give an upper bound, which is a sufficient condition, but not necessary. My conjecture is, yes, there's a similar kind of like ish phase transition for a nonlinear model, but we cannot solve it for now. And also, the last one, I think the answer is basically no. There's no like a universal notion of task similarity. Because what we find, even in the linear case, the task similarity depends on the model to be used. And because that's the ultimate answer we try to see. So given multiple training data sets, can I somehow determine which training data set to be used together to avoid the potential task interference? That means a notion of similarity between tasks. But turns out our answer is it's not possible, and the notion of task similarity depends on the model to be used. And finally, I want to thank all my students and collaborators who work together to try to solve this line of research questions. And thanks everyone again for coming to the talk today.
Thanks for the talk. Any questions from the audience?
So I'm a complete outsider into this field. What have you maybe seen examples like in business applications where you can observe this non-convexness of your search space?
Yeah, actually, we can definitely come up with synthetic example, which those kind of non-convex case appear. But in real world, like a business application, for example, in Google and OpenAI, their model is huge. And when model is huge, this kind of phenomenon does not appear.
And also they don't have enough parameters K that they want to optimize for that.
Right. Usually in practice, K is on a scale of like hundreds, at most 1,000.
Okay.
A number of parameter in practice like trillions. At least billions. Okay. Billions to trillions. Yeah. Okay. So that's much larger. Yeah. So in practice, no one is on the under-parametrized regime.
Okay. Yeah. Thank you. Yeah. Thank you.
Any other questions? Yeah, I have one question. So this time, like loss function. So for example, if loss function has different amplitude, dynamic range, so still this is holds, or is there any constraint for the, like for example, one loss function is like mean square error, the other is like maybe cross entropy.
Right.
So maybe the value can be different. So so in this case, the results can be changed, or? Oh,
it actually doesn't hurt that much because that mainly corresponds to a choice of the origin. For example, if one loss is on the range of 0 to 100, the other is on the range of like 10 to 1,000, it's basically only shift the axis or the origin, but the shape does not change.
Okay, that's
right.
Thank you. You mentioned when the network be enough wide, we don't care about that it's non-convex. Yeah,
as long as your network is wide enough.
Yeah, what's the criteria when we understand that the model is enough wide?
Right. For linear case, we answer basically it's larger equal to k. K is the number of tasks.
And k is the number of tasks.
Right. As long as it's larger equal to k, we don't have the issue. And as long as we are smaller than k, even smaller than 1, we have the issue. But for nonlinear model, we don't have a lower bound. We only have a sufficient condition. And the sufficient condition is also very loose, but it depends on n. But in the linear case, our conclusion is complete. It only depends on k and does not have dependency on n. And it's precisely a phase transition, right?
How about this?
Oh, yeah, that's a good question. Actually, I didn't talk about that part. Let's go to the table. So for linear model, actually the depth doesn't matter because even we have like more than depth of 2, for linear model, that's the same because we can condense all the linear matrix multiplication into just 1. So for linear case, depth doesn't help. But for nonlinear case, actually I can reduce this upper bound by a factor of d. D is the depth of neural networks. But I doesn't win because the number of parameters is still like n times k. Because if I have depth d, then each layer only require n times k divided by d, number of neurons. But I have d layers, so the number of total neurons is still n times k. So I can slightly reduce this one by using more depth, but theoretically speaking, it doesn't help.
That's interesting. Thank you. So any other questions? Oh. 何か
ないです。
質問来てます？来てないです。
ないです。
はい。Okay.
Is there any criteria to define how similar tasks are? For example, every 2 loss would be, we discuss whenever we have, so it doesn't matter loss are, similar or not.
Oh yeah, actually there is. It only matters in the under-parametrized regime, and the task similarity is defined by the inner product between yi hat and yj hat. And the meaning of yi hat and yj hat is the optimal linear prediction from the input. So here is the definition of yik, and the yik is essentially the optimal linear prediction given by this term, and this term only depends on the input x and y. So if the inner product between these two are positive or non-negative, then they're positively correlated. Otherwise, it's negative, right? So that's the notion of task similarity, but only holds for linear model. We do not know what's the task similarity for nonlinear model.
Thank you. And then, okay, so it's already a time. So let's thank the speaker again.